I wanted to, for those who have picked the simulink as your final project and want to do the mechanical system, I wanted to sort of go over the physics with you just a little bit, give you the equation since it's not a physics class, it's a programming class. So we're going to talk about how to apply Newton's laws with an object falling in resistive medium, often called drag. So you can also call this Newton in drag. Resistive medium, on a solid object thrown through a resistive medium can be, the drag can be proportional to velocity or velocity squared depending on the actual velocity. We're going to assume the model velocity as kind of standard. But what it means is that the faster it goes, the more the resistance. So, like I said, we're going to do the case where the velocity is proportional to velocity. So that means our resistance is minus v times v. And the minus sign really means it's opposite of whichever way your velocity is pointing. So it's opposite to the velocity. So let's take a case where we have an object that's going to fall in something like water. There's an old commercial where they used to drop a pearl in shampoo. I think it's called pearl shampoo. And so this is going to fall. We're not including the buoyancy force here, so we're just including the friction and gravity. Things work out a little simpler if you call down positive. Then your velocity is down, your friction is going to be up. That's a little odd because it's going to mean your force of gravity is down. So F equals ma. Here's our ma. And then our gravity is down, that's positive, and our friction is opposite, so it'll be minus bv, where b is our coefficient of friction. So our acceleration, which is the first derivative of our velocity, is g minus b over m times v. Okay, so that's our model. So what we'll do is we'll start with acceleration, being a constant. You know it's g. We'll do that one first, so to speak. Or I should say it starts there because your velocity is 0. We're just going to drop it. And so what will happen is the velocity goes up, the friction gets bigger, until eventually the friction and the gravitational force are equal because the acceleration is 0. That's your terminal velocity. So unlike dropping an object under gravity, which just goes faster and faster and faster, terminal velocity, it starts out with a big acceleration, but it eventually slows down until the acceleration goes smaller until you eventually have a constant velocity. And that's called your terminal velocity, and you get it by setting your a to 0. So in this situation, proportional to velocity, then when we're at terminal velocity, set that to 0, you solve, and you see it depends on the mass and b, the drag coefficient. There are some typical examples. Skydiver has a terminal velocity of about 60 meters a second. Baseball, about 43 meters a second. And you can convert those to miles an hour. Golf ball, different size things have different terminal velocities. Now let's go through the equation. It's just nice and separable. We probably did it in Cal 1. If not, we'll do it here. You might have done it in physics too. Physics also. So your acceleration is dv dt, and that's g minus b over mv. So we replace a with dv dt. We have a first order differential equation. We know g, b, and m, they're constants. V is our variable, t is our variable. Knowing where we're headed, I want the coefficient of v to be 1, so I factor out minus b over m. I divide both sides by the parentheses. I multiply by t. Even though it's strictly not fractions, that works. You can do it a little more formally in calculus and get the same thing. And so my minus b over m is a constant, so let's just integrate dt. We get a t. That's log, that's du over u prime. So that's just log of u. So what we'll do then is make both sides a power of e. And we do that little trick where we break this one up to e to the minus b over mt, e to the c. E, we don't know e to c, so let's just call it k. And then there we have our terminal velocity plus k e minus. So that's our exponential. And we'll notice very similar to what we did if you watch the derivation of the radioactive decay, almost exactly the same. So that's our velocity. Now we use our initial condition that we started at 0. We can sort of relax that if we want, but for now we're going to keep that. If we just drop it, so the initial condition is v of 0 equals 0, so plug 0 in for t, and you can solve for k. It's just minus mg over b, which is your terminal velocity. So if you plug that in, then you get that your velocity is your terminal velocity, 1 minus e to minus t over, and your tau is your m over b. Since you're putting tau on bottom, flip that over. And so there's an exponential growth. It asymptotically approaches your terminal velocity. It's going to take it about 5 of whatever that number tau is to get 99% there. Here's a little simulation. Let's see if we can get that to work. I'm not sure y'all can get to it, so I'll run it here. It's in WebAssign. I don't know if y'all were doing WebAssign in physics. I always did, and that's actually where I got that, was here. WebAssign has some great simulations. So here's the little situation we had. We can drop our ball. We've got control over the mass, the radius, and the viscosity, and we'll drop it. And yeah, you can see that exponential growth. And so what happens is it very quickly, with these numbers, it very quickly gets to its terminal velocity. So most of the time down, it's just cruising at a. Now, we saw the terminal velocity, the bigger the mass, so it's going to get there even quicker. Oh, well, no, a little bit slower. The bigger the terminal velocity, the longer it takes to get there. So that one you can see a little better. You can see it speeding up, but then eventually it's going to hit terminal velocity. So now if you want to find x, you let v be dx dt. Again, you separate and integrate, but we know what v is. So if we integrate the vt times 1, you just get a t. If you integrate this one, integrate e to the u, it's what? It's going to be e over the derivative of this, of the exponent. And therefore, that becomes 1 over tau. It becomes on top. We get the minus sign. And so we get that plus our constant. You can check it, take the derivative, you'll get vt. Drop your derivative of your exponent, so you get your minus. You get your minus 1 over tau for the derivative cancels, and you get vt. So you can factor that out. Derivative c is 0. So that's your x, your equation of motion. If you start at 0 and let the ground be, we're going to call positive down. So we'll start at our x or y equals 0. And so plug in 0 for your time. You're going to find what your c is, plug that back in, and you have your equation of motion. So that's the equations in your simulink model that you're trying to reproduce. So for simulink, remember you have to have an integrator. I think the way I have it set up, you can do, you do the first equation, and you'll get credit for that one, and then that's going to be our velocity, right, which is down here. So that's our velocity equation, and that's your first integration. And then if you integrate again, you'll get your x. There's the summary. There's your v of t and your x of t, where your tau and your vt are. So I just wanted to go through that to make sure everybody's on the same page. Some of you may not be in physics this time. It may have been a while since you had it, or you may have talked about it a little bit differently. So anyway, if you have any questions about how to get those equations, send me an email.